So, here we see that this function has rho has support in this closed unit ball. So, by dilation or scaling we can shift the support to any ball of our choice, and this is done by dilation. So, for epsilon positive, define rho epsilon of x is equal to rho of x by epsilon, and now the support of rho epsilon is the ball, closure of the ball with radius epsilon. Okay. So, if we just write it here, so this is C epsilon. No, I should maybe with it just because I want this integral to be again to be 1. So, this there may be a constant here. So, let me just check that. Here is so for the timing I will just put it here C epsilon. Okay. So, this actually let me write this as this C by epsilon n into this exponential minus epsilon square by epsilon square minus mod x square if mod x is less than epsilon and 0 if mod x is bigger than or equal to epsilon. So, in all these cases we just see that rho epsilon x dx is also 1. So, this is important to maintain this. Okay. So, if you draw few figures of this, so starting with -1 and 1. Okay. So, let me just go for another color. So, -12 for example. I am just showing a one dimensional picture. Okay. So, this one will be like that. So, this is rho half and the rho will be little lower. Okay. So, sorry for that. Okay. This is rho. So, as epsilon becomes closer and closer, this peak will go up and up. So, as an exercise, so it is interesting to see that. So, later on you see the delta function, but before that you can verify. So, the little exercise here. It's good exercise. So, we learn lots about analysis, and that is the heart of this course. So, if f is any function continuous near 0, near x equal to 0, then limit as epsilon tends to 0, this rho epsilon x fx O is equal to f of 0. So, you see always already the nature of averages these modifiers do. Okay. And now we use these modifiers to show that C infinity functions with compact support are dense in LP. Okay. So, before that, so often we require to construct test functions. So, that you will see in this course a lot, which have some required properties. So, at times we want that test function to be to take the value 1 on a prescribed set and 0 elsewhere, but maintain that it is C infinity. Okay. So, such a test function can be constructed in general again using these modifiers. Okay. So, let me just mention one result in this direction. Okay. So, if A is any subset of Rn, okay, so define the epsilon neighborhood of A. Okay. So, you are defined for epsilon neighborhood of a point, but for set also you can define. Okay. So, this is just A plus B0 epsilon. So, you translate every point in A by this open ball. So, this you can write it as precisely. Okay. So, this set of all points in Rn which have distance from A, the set A less than epsilon. Okay. Geometrically you can just see that this, suppose this is A. Okay. So, A epsilon will be, use okay, this is A epsilon including A, of course. Okay. So, that is just translating every point by. Okay. So, now we can state this result. So, as I said, so many of these results will not be proved. These are prerequisites, but just mention or sketch wherever possible. Okay. So, just let me write it as a theorem. So, for any set A in Rn, and epsilon greater than 0. So, you just, these are the prescribed quantities. So, there exists eta which is a C infinity function with compact support. Okay. So, let me state that as part of the conclusion such that, so you will see that it is has compact support. So, eta, let me write it, eta epsilon. So, that depends on epsilon. So, eta epsilon x is equal to 1 for x in A epsilon, that epsilon neighborhood of the set A, and eta epsilon x is 0 for x not belonging to, so a bigger set. So, you take 3 epsilon, okay. And important thing, so it is bounded less than or equal to 1, and these important estimates. So, you will see the usefulness of these estimates when we go to PDs. M alpha for all multi indices. Okay, so let me just quickly recall this multi index notation. So, maybe here. So, a multi index is an n tuple. Okay, so this alpha 1, alpha n, and alpha i's are always non-negative integers. Okay, and d alpha is d by dx1 alpha 1 etc. d by dxn. So, these are partial derivatives. Okay. So, we also use another notation. So, if x is in Rn, x alpha is x1 alpha 1 etc. xn alpha n. Okay, so this is standard notations. So, we will be using that. Okay, so this these are very important estimates. Okay, so often we use this theorem for a compact set in Rn. Okay, so that's so how this is proved. This is, I just mentioned what is this eta epsilon function. So, then you can verify yourself all these conditions. Okay, so this eta epsilon x is integral in Rn, the characteristic function of a 2 epsilon, okay, and rho epsilon x minus y dy. So, you see the usefulness of the modifiers straight away. Okay. So, I just comment here. So, you can just verify all the properties by using this expression. Just a comment about the integral. So, even if A is an infinite set, and since the support of this function, okay, so this, let me write that, support is equal to b x epsilon. Okay, closer. Okay, so the integrand is, the domain of the integral is always a compact set. Okay, so even if it is, so integral, this integrand consists of functions of multiplication of two functions. So, the domain is the common support. So, since one function has compact support, automatically the domain of integration is finite, even though if the set may be an infinite set. Okay. So, this characteristic function may not have compact support, but yet this integral is always finite. Okay. So, rest you can verify directly from this definition. Okay. So, corollary. So, if K is any compact subset of Rn, Rn or even omega. So, let me just is compact. So, often we use this notation instead of writing all the time K is compact. So, we use so this means K is a compact subset of omega. So, omega is an open set in Rn. Then there exists a C infinity function in Rn, of course, such that so 0 eta less than or equal to 1 and eta equal to 1 on K, and okay. So, the other things we need not state. Okay. So, here you have to just take. So, if omega has finite boundary, so you just take 1 by 4 distance between the compact subset and the boundary. Okay. So, omega is here. So, this is del omega, this is omega, and compact subset is here. So, if omega is unbounded, for example, if omega is Rn, so take R large enough such that K is contained in B0 R. So, in that case you take epsilon equal to quarter of the distance between K and the sphere. Okay. So, this let me write that sphere and another notation. So, S0 R is nothing but set of all x in Rn mod x equal to R. Okay. So, now we show that the C infinity functions with compact support are dense in LP. Okay. So, let 1 less than or equal to p less than infinity and f in LP omega. Okay. So, define f epsilon x is equal to rho epsilon star f x. So, let me again write this thing. Dy. Okay. So, rho epsilon being a function of C infinity function of compact support is in every LP. So, we can easily check that epsilon is in LP. Okay. So sometimes these f epsilons are also called modifiers of the function f. Modifiers of f. Okay. So I missed one fact about again convolutions. Okay. So if f is a Cm function in omega, also L1 omega and G in L1 omega, and also this d alpha f in L1 omega. Okay. So this implies this f star g is also differentiable, and this is just given by d alpha f. So this is an important property of the convolution. So if one of the functions defining the convolution is smooth with its derivative again in L1, so we can transform the derivatives of f star g to that function. So it's sufficient that one of them be smooth. Okay. So in our case, this rho epsilon is C infinity function. Okay. So it just this implies that straightway. Okay. So this epsilon is C infinity. So this being the convolution of these two functions rho epsilon and f, and d alpha f epsilon is star f. So we are not going to use right now this important thing, but we are just going to use that this. So we want to show. So this is the theorem. F epsilon is in LP, norm of. See these approximations, so under our control. Okay, so this is very important in applications, and f epsilon converges to f in LP. Okay, so I have just omega is already understood. Okay, so that's okay. So this means norm of f epsilon minus f tends to 0 as epsilon tends to 0. Okay, let me briefly indicate the proof. Proof is not really hard once we use the fact that the continuous functions are dense in LP. Okay, so that's so sketch. So let me just okay. So if P is equal to 1, okay, so this f epsilon x is less than or equal to integral rho epsilon x minus y f of y dy. Okay. So, let me not bother to write the domain, it is understood, it is this ball of radius epsilon centered at x. Okay. So, now you integrate with respect to x this inequality and use Fubini theorem. So, here we are using the fact that this rho epsilon is a non-negative function. Use Fubini's theorem. Okay. So, integral mod epsilon x dx is less than or equal to integral mod fy dy and this rho epsilon x minus y dx. Okay. So, I am already using Fubini theorem, but this is equal to 1 and this is just norm of f is 1. So, this is norm of epsilon. Okay. So, when p is bigger than 1, we use Hölder's inequality. Okay. So, that is so f epsilon x. So, what we are going to do is, so since rho epsilon is a positive function, so this I write it as 1 minus 1 by p x minus y rho epsilon 1 by p okay. So, less than I will. So, using Hölder's inequality, you see that this is rho epsilon x minus y dy to the power 1 by q, and this is just rho epsilon x minus y mod fy to the power p dy and whole power 1 by. So, this is 1 by p plus 1 by q is 1. Okay. So, this is simply the Hölder's inequality. Now, take pth power, both sides, integrate with respect to x, same procedure, and use Fubini. Use Fubini. So, you just get that same computation as the case p equal to 1, except for this little arrangement. Okay. So, you just p. So, as you see more and more PDs, you will appreciate these bounds. Okay. So, next consider, so now we are going to prove that the other part, just namely we are going to show this this part f epsilon converges to f. So, you will also see the techniques what generally employed in this analysis of PDE. We will do it so many times. Okay. So, we want to show that this absolute value to the power p that tends to 0. right. That is what we want to show. Okay. So, this the first step we write is this rho epsilon x minus y f of y minus f of x x dy. Why you can write like this? So, the main property we are using of rho epsilon, that its integral is 1. Okay. So, just so repeatedly we are using that. So, we can bring this fx term inside the integral. Okay. So, again let me not bother about writing the domain of the integral. So, that is fine. So, looking at this thing, so now you realize, so if f is a continuous function of compact support, so we can control this by uniform continuity of f. Okay. So, that is what. So, again use the same computation as we did earlier. So, that implies f epsilon x minus f x to the power p is less than or equal to integral rho epsilon x minus y dy. Okay. So, now we want to integrate with respect to x and show that that tends to 0. So, so first assume, okay. So, there are some gaps here in the argument. So, you should fill in. First assume f is continuous and has compact support. Okay. So, in this case it is very easy. Okay. So, use uniform continuity because it has compact support. Okay. So, a continuous function on a compact set is uniformly use uniform continuity to show that f epsilon minus f p tends to 0 as epsilon tends to 0. Okay. The general case follows from density arguments. Follows from density arguments. I strongly suggest that you should work out these two steps in detail and convince yourself that the proof works out. Okay. So, that is very important. So, in fact, we are going to leave such small arguments for yourself to check throughout this course, because if we keep on doing these things, then we require a lot more time to explain everything. Okay. So, you should do along with us. Okay. So, just we are hinting it, but you should work out all the details. Okay. So, we will see next time we will continue with some more discussion on LP spaces and describe the compact subsets of LP spaces. Thank you.